This is the intro video for AP Calculus AB, section 4.3, and we are going to take what we were practicing in 4.2, and we are going to work on transitioning into what we call the definite integral. So let's review a little bit about Riemann sums. Riemann sum is a collection of approximations for area under the curve. We've been doing a lot of practicing with that in our last couple of classes. Upper and lower, left and right, midpoint. All these different approximations all fall under the category of what we call Riemann sums. So what we're going to do is, thankfully, we are not going to be doing a Riemann sum for every definite integral we encounter. We're going to be able to basically look for a shortcut. We're going to be able to do it a lot faster. So we're going to transition today into that. So I want you to take a look at the expression right here in the middle of this equation. We're going to define the definite integral right here. So this right here, I hope that looks really familiar to you. We have been working with that for quite a while. This is that limit sigma notation, and we look at the what's inside the limit sigma. If you guys remember, f of c would just be the height of a rectangle, and delta x would just be the base length of a rectangle. And so sigma means sum, right? And so we'll be summing up a bunch of heights, and then of course the limit means as the number of rectangles goes to 0, summing up these heights times bases, summing up these areas would actually give us the exact area under the curve. So I hope that that's just a review for you. We've already done several of those already. The notation on the left is new, but it is, I think, pretty understandable. Please note that the f of c and the delta x are the exact same thing. So we're still talking about summing areas of rectangles, but the limit on the end is a little bit different. It says limit as that weird looking triangle expression goes to 0. Let's talk about what that means. That triangle with the double absolute value looking things is the width of the widest rectangle. Width of the widest rectangle. So if the width of the widest rectangle is heading towards 0, then wouldn't that mean that the width of all the rectangles are heading towards 0? And so the f of c is still the height, just like it was before, and the delta x is still the base length, just as before. So base times height is area. So because the widest rectangle's width is going towards 0, that would mean the rest of the rectangle's widths are going towards 0, which means that there's an infinite number of rectangles, which is what we've been talking about. It's just a different expression for it. So those two things are equal. Now here's the big transition. We're going to say that those two summations, those limit sigma expressions, are equal to this right here. The way we would read that is the definite integral from a to b of f of x dx. The definite integral from a to b. So let's point out these different things inside this integral, the integrand here. F of x, that is just a height. It's the height of a rectangle. Dx would be the base length of that rectangle. So it's basically just base times height again in there for the integrand. And then, of course, this, the tall skinny s stands for integral, with the a and b means a definite integral. And so this tall skinny s with the limits, the a to b right there, this is an infinite summation. So if you wanted to boil down what a definite integral is, it's simply an infinite summation of a bunch of areas of rectangles. That's really all it boils down to. So we're gonna explore this a little bit further and do a little bit of practicing with this in this section. So let's go ahead and move on to the next part of this. We've already talked about this, but if you want to get these blanks filled in, let's go ahead and do that. So it says if the width of the widest rectangle is approaching 0, the width of each rectangle is approaching 0. This means that the definite integral is an infinite summation of infinitely skinny or narrow rectangles. Since each rectangle is infinitely skinny, you could informally think of it as we are just adding up an infinite number of heights. So an indefinite integral is a family of functions. This is what we worked on at the start. And what characterizes an indefinite integral, of course, is the plus c that's on the back end of those. And a definite integral is simply a number. You're just going to get, like 3 or negative 12 or whatever it might be. So a definite integral just gives you a number, some kind of value, and an indefinite integral is a family of functions. Okay, so we are going to continue to practice what we've been doing in 4.2. We're going to do it here with number 1. Please carefully look at the instructions. It just says set up a limit sigma expression that is equivalent to the integral from -3 to 1 of 5x dx. And I've drawn a little graph for you over here of 5x dx. It's got some, some area in there as well, but we just have the line 5x. So we're going to try to just set it up. We're not going to take it all the way through to the end. We're just going to set up a limit sigma expression for this particular integral. So as we learned before, we're setting up a limit sigma expression like this. There are some parts of it that are just pretty prescriptive, like they're always going to be the same. So I'm going to put those in here right now. So it's going to be the limit as n goes to infinity of sigma from I equals 1 to n. And then what's on the inside of the sigma, the summation here, that's where it's going to be more customized, right? So we're always going to have this limit sigma thing. Limit as n goes to infinity of sigma from 1 to n. So what goes inside here, of course, is area, like an area formula. And so that's what I'm going to attempt to put in here. So the first thing I'm going to put in is the base length. So the base of each rectangle. So what I notice is that from -3 to 1 is a distance of 4. And I want to fill this distance with rectangles, but I want to be flexible in how many I can put in there. I could use 4 rectangles, I could use 10 or 20 or 30 or 40 or 100, but I want to be flexible enough to pick whatever I want. And so I'm going to say that I'm going to use n rectangles. It's just an unspecified number, so I'm going to use n rectangles, and so that means that the width of each rectangle, the width of each of these little subintervals, would be the total distance, which is 4, divided by the number of rectangles, which is n. So my base length is going to be 4 over n. And then the other thing I got to put in here is my height. And of course, the height is related to the y values of our function. Our function is 5x. And so what I'm going to do is write an expression for height. So the input is x, and my function is 5x. So I'm going to say that my height is going to be 5 times the input. And I've got to think creatively about what the input's going to be. So the input, I'm going to start over here on the left. The lowest possible input I could have here is -3, right? So I'm going to have an input of -3 plus. Now as I move across this picture, I'm going to be, just continuing to add rectangles into the mix. So this and this, so on and so forth. And so as I keep going across the picture here, every time I jump from one rectangle to the next, I'm going to add basically the width of each rectangle. So we already decided the width of each rectangle was 4 over n. And so it's going to be -3 plus a specific number of widths added to it. So I write that as 4 over n times I. This, of course, is the base length, so I'm going to, every time I jump to another rectangle, I'm going to get a 4 over n added to my input, and then the I is there so that I can add a certain number of rectangles. And of course, I want to eventually end up adding an infinite number of rectangles, but having that I there works with the I in my sigma as my summation element. So this would be it. This would be the expression for the limit sigma expression for the integral right there. And at this point we'd stop because it just says write that expression that's equivalent to integral from -3 to 1 of 5x dx. So that concludes our video. As you can see that when you come to class, we'll continue to work with this, setting up limit sigma expressions, and we'll do a couple of questions with those before we move on. So I'll see you next time in class.